So now we want to take a look at Kepler's laws of planetary motion. The motion of the planets is one of the great stories of discovery in the history of science, and how people went from thinking about Earth as the center of the universe to various complex models of understanding how the planets orbit around the Sun is a great story. But for us, we want to focus on what is essentially the final explanation of planetary motion. This was found by Kepler, who figured out these laws using the observations of Tycho Brahe in the early 17th century. Interestingly, these were found before Newton figured out that gravity followed an inverse square law, which was discovered about 60 years later. So Kepler's first law of planetary motion is that the planets orbit in elliptical orbits in which one of the foci is the Sun. So planets do not have perfectly circular orbits, they are distorted. I've put up a simulation for you to play with on the next page. That one is one of my favorite FETs. You can give planets and a satellite different trajectories and see if they crash into the Sun. An ellipse is a round shape where the sum of the distance between two different points, called the foci, add up to be a constant. If the two foci are on top of each other, then it becomes a circle. In the orbit, we call the perihelion the point in the orbit that is closest to the Sun, and the aphelion is the point in the orbit where the planet is furthest from the Sun. Kepler's second law is that as a planet moves in its orbit, a line joining the planet to the Sun sweeps out equal areas in equal times. This one you could be able to figure out, I think. If we think about this, the angular momentum of the planet as it orbits is equal to the moment of inertia times the angular velocity. The moment of inertia is mass times r squared, and the angular velocity is the velocity divided by r. So the angular momentum is going to be the velocity times the mass times the radius. So the velocity times the radius must be a constant due to the conservation of angular momentum. That means if we had an attractive force that wasn't gravity, it didn't even have this inverse square law relationship, Kepler's second law would be correct. This also tells us that the planet will be moving faster as the radius decreases and slow down as the radius increases. This is not so noticeable for a planet, but in the orbit of a comet that is extremely elliptical, where the perihelion is very close to the Sun and the aphelion is very far from the Sun, then the comet picks up a lot of speed as it approaches the Sun, and then it slows down very much as it heads to the aphelion, where the comet is very far from the Sun. Kepler's third law tells us the period of the orbit of a planet around the Sun based on its radius. The period is the amount of time it takes a planet to orbit the Sun and return to its original position. So the period of the Earth is about 365¼ days, and Kepler found that the square of the orbital period is proportional to the cube of the radius of the orbit. This can be derived if you set the gravitational force to be equal to the centripetal force that turns the orbit of the planet. Doing this, you get that the period, t squared, is equal to the radius cubed. This is interesting because it can tell you that the period, so the length of a year of a planet in our solar system, depends most strongly on the radius, the distance of the Sun, and it's independent of the mass of the planet. To find the period, so we use the formula. The period is equal to 2 times pi divided by the square root of the gravitational constant times the mass of the Sun. Strictly speaking, the mass should be the mass of the Sun plus the mass of the planet, but in general the mass of the Sun is so much larger than the mass of any planet, we can just treat this as the mass of the Sun. This sounds good, but is it true? So let's try a sanity check and see if this works out. So our sanity check is we want to calculate how many days are in a year for Earth. We know the mass of the Sun, so that is given. It's 2 times 10 to the 30th kilograms, and the average radius of the Earth's orbit is 1.5 times 10 to the 11 meters. So what does Kepler's law predict? Well, we'll start with our formula. The period is equal to 2 pi divided by the square root of g times the mass of the Sun. So we multiply 2 pi divided by the square root of a 6.67 times 10 to the minus 11 times the mass of the Sun, 2 times 10 to the 30th. Then we multiply that by the radius of the Earth to the 1.5th power, which is 1.5 times 10 to the 11th meters. Okay, so that gives us a period of 3.16 times 10 to the 7th seconds. So we know there are 24 times 60 seconds in a day. So we divide that, which is 86,400 seconds, and that gives us 365.8 days for the periods of the Earth's rotation. And that's pretty good. So all right, I've asked you a couple questions about this. It should be pretty similar to the problem we just did. One is for Mars, and one is for an asteroid. So I guess I had to do one for an asteroid because I guess you could just Google the answer if I ask you about a known planet. All right, good luck with your questions. So on Monday, we're going to look at the potential energy, the gravitational potential energy, and finish our units on gravitation. All right, good luck with your questions, and take care of yourselves.